Hey guys, STAT1800. Much like the previous video, I'm going to link this one into a video I created for my STAT1800. The next video is going to be on z-scores, and you're going to find out that z-scores are really easy to calculate. It's just the score from the distribution minus the mean divided by the standard deviation. And I go into all this in the next video. Now, there are a couple of things that are different, though. This textbook defines outliers. If we have a z-score that is greater than 3.00, or if we have a z-score that is less than negative 3.00, then this is referred to as an outlier. So you can think about outliers have the potential to be any number on the number line. Outliers can be zero. If the score that we're trying to find the z-score of is equal to the mean, then that score minus the mean is 0 divided by any measure of spread, the standard deviation, then our z-score would be 0. So our z-score can be any number on this number line. So if we look at the cutoffs from +3 to -3, any value in our distribution that creates a z-score from -3 to +3 is not an outlier. Anything from -3 down to +3 up, then these are outliers. Now, one more thing before I link into the video. This textbook, at least for now, talks about distribution shapes. And I kind of like the way that the author defines this, because he does so numerically. And he does it according to 3 pretty strict rules. And those rules are, if the mean is greater than the median, then we define our distribution as being positively skewed. If the mean is less than the median, we define this as negatively skewed. And in situations where the mean is equal to the median, then we call this a symmetric distribution. All right, so positively skewed, negatively skewed, and a symmetric distribution. Now, there's a lot more to this than what we're going to assume right now. We're ultimately going to get into looking at histograms, and we'll get a better indication from the graph about the distribution shape. But for right now, for the assignment that we're currently leading up to on my stat lab, this is the criteria that I want you to use to determine whether or not something is positively or negatively skewed. I think that's it. One more thing before, and I think this is a good time to bring this up, because the z-score video is very short. Let's say that we have some ACTs, and we want to well, I don't know, we'll just make some really smart people in there. All right, 3 things I want to talk about here. First thing, we run into quite a bit in statistics things called stem and leaf displays. And what stem and leaf displays do is they take the leading digit and they call it the stem. So the leading digit here would be 2, 1, 3s. So they would have 1, 2, 3. So they take out all the possibilities for the leading digit. And then they put in what's called a leaf. So I can go to 23 and put a 3 there to represent the 23. Put a 4 there to represent the 24. Put a 7 there to represent the 27. Put an 8 up here on the line with 1 because it has a leading digit of 1. So 9, 1, 2. And then 32, 34, and 26. Now, typically I would redo this and have these in ascending order. But not necessary to do that. Easy for you to say. Now, what this does, it gives us a little bit of an indication about the distribution shape. We'll get into more about that next week. But for now, I just want you to know that these things are very easy to find, and they're very easy to create, and they are a method for organizing and representing quantitative variables. Now, something else we run into that I want to just touch on is something called a histogram. And a histogram is really just a picture for a frequency distribution. So histograms begin with some sort of frequency distribution where we have classes and then frequencies of the classes. So if I were looking at ACTs, I may, with this data set, I would probably want to tap into the lowest at 11 and look at the largest at 34, and I would want to create classes that were just a little bit below the smallest and a little bit above the biggest. So I may want to start at a 10 and run this up to maybe 14. So the next class would start at 15. Since this has a width of 4, I would want to go to a 19. This would start the next one at 20, going up to 24, 25, up to 29, 30, up to 34, which takes care of the biggest piece of the biggest measurement that I have. Now you might be saying, well, Dr. Darby, you're going through this awful fast. The reason I'm going through it awful fast is because I'm going to teach you, if you want a histogram, we're going to use StatCrunch. We're not going to do this by hand. We'll create the bins, we'll create the frequencies, we'll do all this using technology, and again, we'll do this next week. But for now, I want you to just have a snapshot, kind of a glimpse into, if you will, what's going on with the histogram. So 10 through 14, so I have 1, 2, 2 measures, so I'll put a frequency of 2. 15 to 19, 1, 2, I guess that's it. 20 to 24, I have 0. No, I have 2. It's comforting, isn't it? 25 to 29, looks like I have 1. And 30 to 34, it looks like I have 2. I think I missed a 26 here, didn't I? 2, 4, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I missed a 26, so apparently there were 2 that went here as well. Now, from the frequency distribution, it would be reasonable for us to look at a histogram. In a histogram, I would put the name and then the frequency on the vertical, and I would run these from 10 to 15 to 20 to 25 to 30 all the way up to 35, because that's what would begin the next bin, the next class. Now this is a really boring, this is what happens when you bring something up on the fly. This is a very boring histogram because we have all the widths at 2. Actually, that would go from here to there, from here to there, from here to there, and the height of these bars is each equal to 2 because I came up with a wacky example. Now, The only reason I'm taking up your time to demonstrate that to you is for the following. There's something called a frequency, a cumulative frequency polygon. And I have to tell you, I've been teaching statistics now for, 29 years. I've taught sections of statistics over 100 times at Shawnee State. I have never taught the cumulative frequency polygon, but I'm doing it here. So what happens with the cumulative frequency polygon is it takes the values from the histogram, and we will look at the midpoint of each bin. So the first bin was 10 to 15, so I would have a 12.5, and then I would have a 17.5, and then a 22.5, and a 27.5, and then a 32.5 would be the midpoint. So again, what's the midpoint? This class right here runs from 10 to 15. The midpoint between 10 and 15 is 12.5, which I've given right there. The next bin we run from 15 to 20. The midpoint there would be 17.5, so I represent that there. Now the cumulative frequency polygon looks like this. We start out at the midpoint, and we see that we have 2 in that first class. Going to the second class, we see that we have an additional 2. So ultimately, this thing keeps a running total of the cumulative frequencies from the histogram. It would have been just as easy if you're someone like me who is more impressed numerically. You could do a cumulative frequency out here. So you have 2, plus the next 2 is 4, plus the next 2 is 6, plus the next 2, getting all the way up to 10. Now again, it's kind of boring because I came up with a wacky example where all the frequencies within the classes were 2. But imagine if we had something more interesting. Maybe our classes and our frequencies maybe look like this. So the cumulative frequency would start out at 2. We would add the 3, so we have a 5 total by the time we get through our first 2 bins. 7 gives us 12. Get through the next 3 classes, 21, 32, and 47. The reason I'm not making a lot out of this, and the reason I'm going over it pretty quickly, is there's just really not a lot to make of it. There just really isn't. But there's one question, kind of, just to get you thinking about histograms and these cumulative frequency polygons, just to get you thinking about what they, the advantages they have in displaying quantitative variables. I included one on your next homework assignment. But again, there's not a lot going on here. And when it gets to the point where histograms are really a major deal for us, I'll create a video that'll go through it in much finer detail. All right, gang, I'm going to shift you over to the z-score video that I created for 1150. All right, so take care. Okay, guys, STAT 1150 again. We're going to study something called z-scores. The goals of this video are pretty straightforward. First of all, I want to show you the formula. I want to show you how to calculate and interpret a z-score. Next thing we'll talk about is how we can use it, a z-score to detect unusual scores. Unusual usually means extremely high or extremely low. And then we'll look at an example how to calculate a raw score given its z-scores. So let's say something, let's say we have some summary statistics already taken. And let's say that I am focusing on ACT scores for students in my online stats class. And let's say that I've calculated this and I have 31 students in my class. The mean ACT is 21.8 and the standard deviation is 5.2. So what we can do with z-scores is, well, the primary function of a z-score is to determine how far from the mean in standard deviations that a score falls. Now, it's really not fair to just look at how far a score falls from the mean, because we have this measure of variation that determines being close or a long way away. For example, if the standard deviation gets bigger, then let's just look at an example. The standard deviation is 5. If I add 5 to this, then a score of 26.8, or if it's 5.2, it'd be 27, is one standard deviation above the mean. But if I have a standard deviation of 10, add 10 to that, then 31.8 is one standard deviation above the mean. So when we're measuring how far something is from the mean, we need to consider a standardized unit in terms of the standard deviations away from the mean. Well, put all that together, you get the z-score formula, which is just to take the raw score, which in this example would be a student's ACT score, minus the mean over the standard deviation. So guys, the way this would work, the z-score for a student with an ACT of 28. So since the ACT is what we're focusing on, we can say that this is x equal 28. So therefore the z-score would be x minus x bar over the standard deviation. So our x in this case is the score again. We're trying to calculate the z-score of. The x bar, I think I said 21.8. And the standard deviation, I think I said 5.2. So when we put this in our calculator, we would need to put the numerator in parentheses. Let me clear this out so you guys can see. So 28 minus 21.8 divided by 5.2 gives me 1.19. This tells me that a score of 28 is 1.19 standard deviations above, because this is positive, the mean. Not too bad, right? What is the z-score for an ACT equal to 16? I don't know why I'm having such a hard time remembering the mean and the standard deviation. Guess it's a bozo moment. So put in the score of 16 minus 21.8 over the standard deviation of 5.2. So guys, really right here, all I need to do is just go second function entry. And the only thing I need to change is just to 28, from 28 to 16. And you'll see that we get a negative z-score here of negative 1.12. Now, why is it negative? Well, it's negative because the score is below the mean. So we can kind of make a generalization from this, can't we? If the score is bigger than the mean, then this is going to be a positive divided, standard deviation has to be positive. So this is going to be a positive divided by a positive, give me a positive z-score. If the score is below the mean, then this subtraction right here is going to give me a negative number divided by a positive, gives me a negative number. So we can summarize by saying a score of 16 is 1.12 standard deviations below the mean. What if a student has a z-score of 21.8? Now you might say, Dr. Darbro, you can't have an ACT of 21.8, the fall of 19, 20, 21. Let's just pretend, okay? So our z-score is 21.8 minus the mean of 21.8 divided by the standard deviation of 5.2 is 0. So this tells us that the score is no standard deviations above or below the mean because the score is exactly the same value of the mean. So our interpretation, we would say that an ACT of 21.8 is 0 standard deviations above or below the mean in standard deviations, of course. So guys, if we have a mean of 20 and a standard deviation of 5, I can tell you that a score of 18 will have a negative z-score. Why? Because it's below the mean. A score of 25 will have a positive z-score. Why? Because it's above the mean. And a score of 20 will have a z equal to 0 because that score is precisely equal to the mean. Pretty easy stuff, right? Bet you hope it stays this easy. Now, let's say that we have the following. An ACT has z equal to 2.00. What is the value of the ACT if the mean equal 21 and the standard deviation equals 5? So guys, again, the formula is what? The z-score is the score minus the mean over the standard deviation. So we know the value of the standard z-score here is 2. We want to know the value of the ACT, which we don't know, so we'll let that be x. We know the mean is 21, and we know the standard deviation is 5. Guys, multiply both sides by 5. So we get 10 equal x minus 21. Add 21 to both sides. So x in this case would be an ACT equal to 31. So the ACT that has a z-score of 2, and we have this mean and this standard deviation, is equal to 2. Now, I want to go to Blackboard, and I want to show you something that I've uploaded and something we'll do quite often. So if you go to Content, you can see that there's a new folder called Datasets. And I've uploaded a data set, and I'll upload even more, called IQ and Read. So I'm going to open it up. Maybe. don't want to do any of that just yet. All right. All right, so I have this this data set that gives a reading score, an LSS score, the ACT, the student's IQ. This is a reading estimate, their gender, and we have the school district from which the student is taking classes. Now I want to take File and I want to save this on my desktop. And I just want to save it. Now I want to do some stuff with it. I want to get out of this, and I want to minimize this, and I want to minimize this, and I want to go to Google Chrome, and I want to go to my Stat Lab. And once I get to my Stat Lab, I want to go to StatCrunch. I want to go to the StatCrunch website. And I want to select a file on my computer. Choose the file. I put it on my desktop because I wanted it to be easy to find. And then I want to come all the way to the bottom and I want to load the file. Okay, now that we have our data in StatCrunch, we can easily go through and calculate the z-scores. So to do that, we're going to go to Data, Compute, and use Expression. Now the expression we're going to build, and so what I want to do here is I want to take, go over to Build, and I want to take a left parentheses. I want to take read minus the mean. Let's go find it. And I want the mean of read. And then I want to, let's see, I want to divide that by the standard deviation. Where is it? I guess it's right there. Of read. I can, let's see, value's 10. I don't know what that means. So let's just go OK. And column label, let's call that Z for read. And go compute. Now, we've got new columns been added, and you can see that the Z reads over here, you can see that some are negative and some are positive. Now what we can do is we can go to Stat in Summary Stat and do a column and just take a look at read. Okay, so I want to look just at the mean. So the mean is 59.6, so you can see that the read score of 94 is 1.48 standard deviations above the mean, which is 59.6. So all of these values here that are below 59.6 will have negative z-scores. All of them. And any line that has a value below 59.6 will have a positive z-score. Now, so what we can do is we can come in and do a quick summary stats just to follow up on something I talked about a little bit earlier. And we can take this z-read, and I just want to do the sum of the z-read, just to make a point, because the sum of z-scores is always 0, but if you're not careful, it can turn out to be a little weird looking. Now, when you look at that, it's so tempting to look at that sum and say, well, it's negative 1.55. Well, it's not, because within rounding, we have of a total value that is very, very close to 0. This e to the negative 1/5, that's scientific notation. That tells us that we have to move this decimal place 15 places to the left and fill in with 14 zeros. So guys, within some numerical accuracy, well, within some rounding, we can see that the sum of the z-scores is actually 0. So just a point to ponder. Don't spend too much time pondering that. So keep this data set handy. I kind of want to get rid of some stuff for future use. I've got some things that popped up because of some errors, but you know, the z-scores again are very, very easy to find. And again, just as a summary, what do z-scores tell us to do? They tell us to take the score, divide them, subtract the mean, and divide by the standard deviation. Ultimately, a z-score tells us how far above or below a raw score falls from the mean in terms of standard deviations. Gang, that's all I've got in this video. We're going to be our focus about midstream in this semester will change from focusing on samples to taking a look at populations. Now, when that happens, we get into you know, types of different things. Get into different notation for z-scores a little bit. Get into a little different formula with different symbols. But we'll cross that bridge when we get there. So take care.